In my next paper pointer example, I would like to try p equals x. This is also not a complete statement, so this is an expression. The result of an assignment typically result in the value that's being assigned. However, in this example, if you think about the data types of the left-hand side and the right-hand side of this assignment is this: int asterisk equals int. Such assignment is illegal, so this will not compile. So we can just say that this is an illegal attempt to assign a value, an integer value, to a pointer, which is a different data type. The pointer, to be able to be successfully assigned, requires an address type and not an integer type. So this is illegal. You can just write here that this is an illegal expression. We can fix it by using p equals address of x. Of course, this is also an expression. And this time we're taking address of x, which is a0 in our demonstration right here. So we can just replace 0 right here with the value hexadecimal a0. So of course the result of this assignment, the numeric value that's being used in this assignment, is the address of x, which is this. I can fill in. And the data type, of course, is address of an integer on both sides. This is an address of x, and p itself is being declared as the data type that stores addresses of integers. Number 6. You can try integer pointer q equals p. Again, let's start with the language construct. This is a complete declaration that declares another pointer in our fragment of memory. So let's assume that this pointer is placed somewhere in the next available memory. So we'll say that this is our pointer named q, and of course it has the same size as other variables that we've used prior to this, and it's taking an initializer, which is p, and of course p is another pointer which already has been initialized with an address pointing to the location of variable x, which is a0, and therefore we can just safely assume that this will also be initialized to a0. So once again, the numeric value that's being processed here by this declaration, again, is the same address that we've seen before, and of course the data type clearly is stated right here. So this is again the data type that we're using in this declaration. Number 7. You know that you can increment and decrement pointers. So when we increment and decrement pointers, their values are adjusted just like integers, but the pointer knows the kind of data that it's pointing to. And because of this, the pointer will change its value that accounts for the size of the data type that this pointer is designed for. So if we increment pointer q, this pointer will assume that it's trying to relocate its value, its internally stored address, from this integer to the next integer in computer memory. You can see that the next integer has a location which is A4. So this will change the value to A4. And again, this is an expression. And of course, the value that's being manipulated here, the data type, is still an integer that we're trying to, a pointer to an integer that we're trying to manipulate. The resulting outcome of this expression is, of course, the new value that pointer q gets. So I'll just write it right here. A4. As a side note here, I just want to add that this is probably a very bad idea to increment q. Why? Because initially it was pointing to an integer, and now it's pointing to a new data type, which is the pointer. So basically its address is the address stored by pointer q is pointing to an object that has nothing to do with an integer. This is another pointer. So it's probably not a good idea to increment pointer q. The compiler will not stop you. It will do what you're trying to do, but this is now quite dangerous to have a pointer like this, which is now pointing to an object that has nothing to do with its original data type. So that is an example of a bad use of legal but still instruction that could produce dangerous results if we try to use this new pointer. Let's try the next example, number 8, which will be q minus p. Q minus p. Of course, this is also not a complete statement, so we'll just say this is an expression. Now, it's possible, part of the pointer arithmetic, it's pointer to take one pointer and subtract another pointer from it. The result will be the number of elements that reside between these two addresses in memory. We can see that the pointer q was originally declared as pointer to an integer. So the q knows that it's designed to store locations of integers. If we take A4 and subtract A0 hexadecimal value, the result is 4. Numeric result is 4. However, 4 bytes. The difference in address A0 and A4 is 4 bytes, because we need 1, 2, 3, 4 hops to move from A0 to A4 in this memory. So the difference between the two is numerical value 4, but 4 is actually the size of an integer. And when you subtract one pointer to another to find out the difference, it returns the value in terms of elements and not bytes. So the outcome of this will be 1. In other words, this 1, the meaning of this 1 is that these two pointers, p and q, are one element apart, or one integer apart, because both of these pointers are pointing or designed to point to an integer types.